So today's video concerns predetermined regressors, which are also known as sequentially exogenous regressors. This video is a part of a series of videos on the linear unobserved effects model for panel data. We've already talked about the fixed effects and first differencing methods, as well as the random effects approach to estimation and the Hausman test. So today we'll talk about estimation under weaker assumptions, or rather the problems that arise if we only have weaker assumptions satisfied. Then we'll round off this block concerning the linear unobserved effects panel data model by talking about various methods for estimation under weaker conditions, specifically using IV methods next time. So the starting point here is still the unobserved effects model or linear unobserved effects model for panel data. But before introducing additional assumptions, let's just pause for a second to discuss the type of assumptions we've already invoked. So here's a list of various assumptions used for identification and/or consistency arguments. If we are interested in using an OLS, or specifically pooled OLS approach, it suffices that we have a contemporaneous version of exogeneity in play. That is, it only requires that conditional on the individual effect and the regressors in the same period, the idiosyncratic error has conditional mean zero. At least if we're willing to top that up with an assumption that the individual effect is uncorrelated with the regressors in all time periods. Recall that this is the long vector of regressors stacked over all time periods. Now, on the other hand, it is possible to allow the individual effect to be correlated with regressors, at least in some time period, if we're willing to assume or make an assumption of strict exogeneity. Note here that now we've added the regressors in all time periods, or regressors in both past and future time periods, to our list of conditioning variables. That would lead us to a first difference or fixed effects type of approach to estimation. Still invoking this strict exogeneity assumption, if we're also willing to assume that the individual effect is uncorrelated with the regressors, we could take a random effects approach to estimation. And under additional assumptions, this approach to estimation would be efficient. A random effects type of assumption might be one way to proceed if we're interested in estimating coefficients on time-invariant regressors, as these are washed out in the first difference or fixed effects transformations. So at this point, we're going to ask ourselves the question, is the strict exogeneity assumption a strong assumption? And is it in fact too strong? Well, we know that it's certainly restrictive in that it implies that the idiosyncratic errors in a given period, or in any given period, should be uncorrelated with not only past and current values of the regressors, but also future regressors. Now, this need not be a plausible assumption to make, depending on the type of interpretation we would endow these idiosyncratic errors with. And we'll see that in some models it's not even possible. Specifically, in some models, it may be reasonable to believe that the current idiosyncratic error will affect future regressors. So it seems reasonable to introduce a less restricted notion of exogeneity. And that's what we'll do next. So the outline for the rest of this video is as follows. We'll introduce the notion of sequential exogeneity next and discuss it in a couple of examples using a dynamic model as well as a static model with feedback. Then we'll take a look back at our previous estimation methods, namely the fixed effects and first difference estimators, under the assumption of sequential exogeneity alone, and we'll show that they are, in general, inconsistent. In the last part of the talk, we'll then discuss various empirical strategies for remedying this issue of inconsistency using alternative estimators. First on the platter, sequential exogeneity. So sequential exogeneity is defined as follows. We'll say that the list of regressors in all time periods is sequentially exogenous, conditional on the unobserved effect, if the current idiosyncratic error, conditioning on not only the current set of regressors, but also all past regressors, as well as the individual effect, has mean 0. If so, since sequentially exogenous conditional on the unobserved effect is simply too long to say, we might just call the regressors sequentially exogenous or say that they are predetermined. One implication of an assumption of sequential exogeneity, going off our linear model, we see that it implies that the conditional mean of the outcome in period t, conditioning on both current and all previous regressors and the individual effect, is only a function of the current period's regressors and the individual effect, and in our case, a linear function. Hence, the assumption of sequential exogeneity implies that upon controlling for the individual effect and current period's regressors, no past regressors help predict the current period's outcome, in the sense of entering its conditional expectation function. Now it's natural to ask at this point, does sequential exogeneity allow for dynamics or feedback? Well, that's the next topic we'll bring up. So let's take a look at a particular instance of a dynamic model, namely the first order autoregressive model. So in the first order autoregressive model, we model the outcome y as a linear function of the lag of itself up to the unobservables, the individual effect, and some idiosyncratic error. And now we're assuming that the idiosyncratic error in period t, conditioning on not only the individual effect, but also all previous outcomes, is equal to 0 in mean. Now, in order to relate this model back to models in our previous notation, note here that our regressor vector for this model, which in this model is a scalar, our regressor vector can be written as simply the lagged outcome, or lag-dependent variable. You may ask, why should we pay any attention to a first-order autoregressive model? Well, one question one might ask, or use the autoregressive model to address, is whether, upon controlling for the individual effect, does last period's outcome help predict next period's outcome, or the current period's outcome? That is, does the series of outcomes exhibit a sort of state dependence? The answer, using the model, the answer to this question is yes, provided the coefficient on the lagged outcome, rho, is non-zero. All right, so we've assumed that the idiosyncratic errors given the individual effect and previous outcomes has mean 0. But are the outcomes, as implied by this model, in fact strictly exogenous? If so, that would justify a fixed effects or first difference approach. again, the question that we seek to address here is whether the idiosyncratic error in any period, given the individual effect, and the list of outcomes in all periods, whether it has conditional mean 0. Well, let's take a look and see, let's examine the next period's set of regressors, which in this case is just our scalar variable, given by this period's outcome. Then the correlation between this period's idiosyncratic error and next period's regressors is given by the following expression, where we've substituted in for this period's outcome. Opening up the parentheses and distributing the expectation onto each term, we get this second line. And if we now invoke sequential exogeneity, we see that both the first expectation and second expectation are equal to 0. This follows from applications of the law of iterated expectations. Hence, we're left with this last expectation, which amounts to the variance of the idiosyncratic error, and is therefore positive, at least in general. Now, if we were to make an assumption of strict exogeneity, then we would see that the covariance between this period's outcome and this period's idiosyncratic error would have to be 0. This follows again from the law of iterated expectation, where we see that the inner expectation is 0 under strict exogeneity. Well, we've just shown that if that's the case, then the left-hand side here would have to be 0, which is not. So strict exogeneity is not allowed for in this type of model. More generally, whenever we examine models involving lagged-dependent variables, that is, previous periods dependent variables, or Ys, appear as regressors that appear on the right-hand side, then it explicitly rules out strict exogeneity. That is, it is in conflict with strict exogeneity. So we've seen that strict exogeneity is ruled out in the first order autoregressive model and in models with lag-dependent variables more generally. But what about an assumption that the lagged outcome is uncorrelated with the individual effect? Such an assumption, combined with our previous sequential exogeneity assumption, would justify using an OLS, or specifically a pooled OLS approach. Now, so the answer to this question is unfortunately no, since at time t-1, the outcome, or lagged outcome, appears on the left-hand side. Hence, it must necessarily depend on the individual effect. Now we see here that, now one may see from the model that if the individual effect is not controlled for, then persistence in the sequence of outcomes may be due to the individual effect, and one may therefore conclude incorrectly that this persistence arises due to the presence of the lag-dependent variable. If so, we say that we are in a case of spurious state dependence. So we still need to handle the individual effect. It's not somehow magically handled just because we're looking at a dynamic model. It's still a problem. Next, we'll look at a different example of a model, namely a static model with feedback. So in this model, we're modeling the outcome y as being linear in a set of regressors let it be zi, as well as a scalar regressor h up to unobservables. Here we're assuming that the zi's are strictly exogenous, so here we're conditioning on zits in all time periods, but the hi's are only sequentially exogenous. Again, all of this is conditional on the individual effect. Now, suppose here, or to be specific, let's specify an equation for the HIT. Let's suppose that it's influenced by last period's outcome, or past outcomes, specifically last period's outcome, also through a linear relation. So here we're still allowing for the regressors, the CITs. We are allowing for the CITs to also affect HIT alongside an individual effect and a idiosyncratic error which may be different from the one in our outcome equation or Y equation. You may ask, when is such a model relevant? Well, this type of model has been used in the past to analyze both several have been used for empirical analysis in several cases. For example, it has been used to model the relationship between HIV infections and condom usage, where condom usage in the past certainly affects one's propensity or one's likelihood of contracting the HIV virus in the future. It has also been used to model the relationship between research and development expenditures and patents awarded, and as we've already discussed in a previous example, there are reasons to believe that one's female labor supply or one's labor supply feeds back to fertility decisions into the future. Again, we'll ask ourselves the question, given our current specification or current model, are the HITs in fact strictly exogenous? Well, let's just consider next period's HIT, which is a member of the set of regressors for next period. Given our expression for HIT, we may substitute it for HIT, as we've done here, open the parenthesis, and distribute the expectation to each term. Now we see here that several expressions pop up. Well, we can immediately shut down two of these expressions by using our assumption of strict exogeneity of the CITs. Right? This follows from applications of the law of iterated expectations. So we're left with just the sum of two expectations, one involving the outcome and one involving next period's idiosyncratic error in the H equation. Now it's reasonable to assume that the idiosyncratic error in the H and Y, the idiosyncratic errors in the H and Y equations are unrelated. If so, this second expectation is 0. Nonetheless, in order to show that next period's HIT is uncorrelated with this period's disturbance, we still need to show that the outcome and idiosyncratic error in the same period are 0. However, substituting in the outcome, opening up the parenthesis and distributing the expectation, we get the following sum of 4 terms. Now we see here again that we can shut down several of these terms. Now using a combination of strict and sequential exogeneity. Hence, we're left with the latter term, which is the variance of the idiosyncratic error and is therefore positive in general. Hence, in this type of model with feedback, one cannot expect next period's HIT, the sequential regressor, or sequentially exogenous regressor, to be uncorrelated with this period's disturbance. So we should conclude from this example that feedback effects in general rule out strict exogeneity. Next, we'll take a look at our dear old friends, the fixed effects and first difference estimators, under the assumption of sequential exogeneity alone. First up is the fixed effects estimator. So recall that we may express the difference between the fixed effects estimator and the parameters we're trying to estimate as the product of two terms, one involving the average of the average product of the time d-meaned regressors. So these are T by K time d-meaned or within transformed regressors. And the second part of the product here involves the average of the product of the time d-meaned regressors and the idiosyncratic errors stacked over time. Invoking the rank condition of fixed effects and the law of large numbers alongside a product rule for probability limits, we may therefore show that the difference between the fixed effects estimator and the parameters we're trying to estimate converges in probability to a product involving two expectations. Again, we're primarily interested in the second of these expectations, which, if we flesh out the inner product here, we see that it involves a summation over time, such that this latter expectation can be written as the sum of expectations involving the expectation of the product of time period specific time d-meaned regressors and idiosyncratic errors. Hence, for sufficiency of the fixed effects estimator, it suffices that each of these summands is zero. That is, they're zero regardless of the time we're looking at. All right, so let's take a closer look at, say, the teeth summand. Now the teeth summand, which I've repeated here, going back to our definition of a time d-meaned regressor, recall that the time d-meaned regressor is simply the original regressor upon subtracting the time average. The time average was the average of the regressors over time. We use a different subscript, say S. Now, so substituting in for the within transformed regressor or time d-meaned regressor and distributing the expectation onto each part of the difference, we get this expression. And note here that the first part, or the first expectation here, involves regressors and idiosyncratic errors from the same period, which means that it vanishes under our assumption of sequential exogeneity, implying contemporaneous exogeneity. Now the second, hence we're left to deal with the second expectation, that is the mean of the time d-meaned regressors multiplied with the idiosyncratic error in period t. However, as the time d-meaned regressors averages over all time periods, as we've just recalled, if we substitute in the definition of the time d-meaned regressors and distribute the expectation onto each part of the average, we get an average of expectations. Now we know that under sequential exogeneity, UIT given XIS is equal to 0, provided S is in the past, right? Or at least not in the future. Hence, from this average, we can kill all the terms involving regressors from the present or past. And what we're left with is a sum of future values in time. However, given our current set of model assumptions, there's no reason to believe that these are 0. This is not implied by our model at all, so we cannot expect them to be 0 in general. So from this analysis, we should conclude that under sequential exogeneity alone, the fixed effect estimator is inconsistent. So we've just argued that the fixed effect estimator is inconsistent under sequential exogeneity alone. And if we collect our arguments from the previous couple of slides, we see that its probability limit is given by the parameters that we wish to estimate, plus some additional term, where here I've written out this expected product of time-to-mean regressors and this expected product of the time-to-mean regressors and vector of idiosyncratic errors using the sum over time that's built into these matrix products. And also I've multiplied and divided by t in order to write these two terms as involving averages. Now, without additional assumptions, we know the fixed effects estimator is inconsistent, but suppose that we were to actually add additional assumptions, and suppose specifically that we were to restrict or place assumptions on the sequence of regressor idiosyncratic error pairs over time for a given individual, that is, a time series. Now suppose that we would assume, if we were to assume, that this time series for each individual is so-called weakly dependent, then one may show, and this lies outside the scope of this course, and I won't hold you accountable to any sort of calculation involving weak dependence, but one may show that this average, which pops up as a source of inconsistency, is of order big O t minus 1 as the length of the time series grows without bound. Hence, one may conclude that under this additional assumption of weak dependence, the inconsistency of the fixed effects estimator is of order big O t minus 1, again, as the time series grows without bound, or the length of the time series grows without bound. Now, a formal definition of weak dependence, again, lies outside the scope of this course, but intuitively, weak dependence means that the further two random variables are separated in time, the less dependent they are of each other. And as this time gap increases, the dependence in fact vanishes. However, these limits, this sort of asymptotic analysis as the time series dimension, or what we may think of as the panel dimension, grows large or grows without bound, doesn't really fit into our assumption of having t being small. Hence, under our working assumptions of, or within our regime of a large cross-sectional dimension and a relatively small panel dimension, the fixed effect estimator remains inconsistent. What about the first difference estimator? How does it behave under the assumption of sequential exogeneity alone? Okay, again, one may rearrange or plug in the model and show that the difference between the first difference estimator and the parameter we're trying to estimate can be expressed as the product of two terms. Here we're dealing with the average of the difference regressors, where now this delta boldface xi denotes a t-1 by k matrix of the xits, or rather the differenced xits. There's only t-1 rows because we lose one period of data upon first differencing. And here, this delta boldface ui denotes a t-1 by 1 vector of the differenced disturbances. Now, invoking the first difference rank condition, a law of large numbers, and the product rule for probability limits, we may show that the above product converges in probability to the corresponding product upon replacing averages with expectations. We're primarily interested in the second part of this product, since it dictates whether or not the estimator is consistent. So expanding on this product, we see that the inner matrix product can be written as a sum over vector products where we're summing over the time index. So polling, we may expand on this product, write it as a sum, and distribute the expectation onto each summand. This latter expression shows that if we want the left-hand side to be 0, it suffices that each of the right-hand side summands is 0, which means that the differenced regressors should be uncorrelated with the differenced idiosyncratic errors for all time periods. Is that the case or not? Well, let's plug in our definition of differenced regressors and definition of differenced idiosyncratic errors, and then open up parentheses and distribute the expectations to see that we are really dealing with the sum of 4 expectations. Now, 3 of these expectations involve expectations of products between variables from the same period, as these two are, or products between an idiosyncratic error and a regressor from the past. Hence, under sequential exogeneity, all of these 3 terms are 0. So we're left with showing that the expectation of the current regressor times last period's disturbance should be equal to 0. However, our model doesn't restrict this relationship in any shape or form, so we cannot expect this vector to be 0 in general. So from this analysis, one should conclude that under sequential exogeneity alone, the first difference estimator is inconsistent as well. And similarly, we may write its probability limit under sequential exogeneity as beta, the coefficients we're trying to estimate, plus the product of 2 terms, where again I've fleshed out these expressions from previous slides. using the summation over the time index. Now, what's important here is that even if we're willing to make an assumption that restricts the dependence across the time index, such as a weak dependence assumption, then this latter average need not vanish as the length of the time series grows without bound. That is, the panel dimension becomes large. There's no reason to believe that this should go to 0, even though we have a very long panel. Hence, as opposed to the fixed effects estimator, or our analysis thereof, the inconsistency of the first difference estimator is not alleviated by having a long panel. So even if we were to believe, even if we were to believe or were to have access to a long panel, it wouldn't help us if we were to use first differencing. Hence, up to this point, one may view the fixed effects estimator as having a slight advantage compared to the first difference estimator. However, this advantage is only relevant when we're dealing with long panels, which we're not assuming access to in this course. Next, let's discuss alternative empirical strategies, which allows us to estimate the models using only sequential exogeneity. Now, as already discussed in our analysis or look back at the first difference estimator, with sequential exogeneity alone, we can't rely on the differenced regressors being uncorrelated with the difference disturbances. So we'll have to do something else. And here in this class, and for now and for next lecture, we'll try to search for other orthogonality conditions which will suggest instrumental variables. We may then use these instrumental variables for the purpose of estimation in procedures akin to two-stage least squares. Or we may, in an attempt to achieve more efficient estimators, use more advanced methods using the procedure of generalized method of moments. Now note here, as a first step, note that the the first difference approach has one advantage, in that upon computing or transforming the variables using the lac transformation, or first difference transformation, we only introduce correlation within one lac, or one period of time, where in reducing the left-hand side here to the right-hand side, I've invoked sequential exogeneity. It's much more problematic to attempt to salvage the fixed effects approach, since within transforming, or time demeaning, involves regressors in all time periods. So for the rest of this lecture and the lecture to follow, we'll focus on attempting to salvage the first difference approach. So what kind of instruments could we come up with, or could we construe, for the purpose of instrumenting the differenced regressors? Well, we may notice that under sequential exogeneity, the regressors in all past periods can be shown to be orthogonal to the difference disturbance. This follows from plugging in the definition of the difference and distributing the expectation onto each term, only to realize that these expectations are both 0 whenever we're looking at a period S which is in the past. That is, it is at most t minus 1. Hence, at time t, for the purpose of instrumenting the differenced regressor, the available instruments we have are given by the list here, xit-1 O, where this superscript O notation, when combined with a subscript T, denotes the list of all regressors up to and including period T. So the available instruments we have for the differenced regressor are given by the regressors in all past periods. Note that this list of regressors, the regressors up to and including period T, is a lowercase t by k vector or row vector to be specific. Now, if these elements are all valid instruments, then by appealing to the law of iterated expectation, one may show that really any function of these elements are valid instruments too. Now, this suggests a way of coming up with instruments in our differenced equation, but I do want to stress that there is a potential issue with this procedure, and it goes to the heart of it goes to one of the assumptions underlying the instrumental variables approach, namely the relevance assumption. One issue one may face in practice is that the differenced regressors may have little correlation with past regressors. And if so, we say that we face a problem of weak instruments. Now, the weak instruments concern is discussed in the book, but it lies outside the scope of this course. I only want to mention it since it is a problem which is likely to pop up in practice. So for the rest of this talk, we'll spend some time seeing how we can develop orthogonality conditions and come up with instruments in a particular example model, namely the autoregressive model, or first-order autoregressive model. Here I've just restated the model for convenience, where we still have to deal with this individual effect. Our method for dealing with it will be to compute the first differences, thus canceling out the CIs. Hence, our estimating equation is stated in these first differences, where we now have capital T minus 1 periods of data available. Now, using sequential exogeneity of the outcomes, which now amounts to the past outcomes, since our only regressor is the lagged dependent variable, one may show that the covariance between the difference in outcomes or lagged outcomes and current difference in disturbances or idiosyncratic errors is given by the variance of the lagged idiosyncratic error up to a sign. Hence, it is non-zero, which means that the difference in lagged outcomes is an endogenous variable, and we need an instrument. Now, this model, or an autoregressive model, or first-order autoregressive model, has been treated in the past by several authors, specifically Anderson and Shao in an 1982 paper, suggest using pooled IV, pooled instrumental variables estimation of the first difference equation, using just a single instrument, as given by the twice lag outcome, or perhaps the twice lagged difference in outcome, as suggested by first differencing. Another approach was suggested by Arlano and Bond in the early 90s, where they devised a method known as efficient or full generalized method of moments, where they use all the available instruments that are available at any given time period. In this first-order autoregressive model, the relevant instruments, which would correspond to xit minus 1, O, all of the past regressors, are given by all of the outcomes up to and including period t minus 2, by which I mean that these variables are available for instruments for the difference in the lagged outcome. Since all of these past outcomes up to and including period t minus 2 are available as instruments, functions of these variables are valid instruments as well. In particular, the vector of lagged outcomes, or lagged difference outcomes, up to and including period, or the vector of difference outcomes up to and including period t minus 2 would also serve as valid instruments. In the next lecture, we'll go into more detail about how one may actually implement various instrumental variable procedures in practice, and therefore come up with estimators for the first difference system.